Good evening and welcome to tonight's lecture, the first of this academic year. I'm George Kraw. This evening we will be having really a fascinating discussion about the evolution of the universe and what its prospects may be, being delivered by Professor Alexie Leauthaud, and I hope I pronounced that right. I'm terrible with French names, but she will be talking to us tonight, and she will be introduced by Professor Alexie Leauthaud, who is the Associate Director of the Astrophysics Institute, Kraw Institute for Particle Physics. But before we start, I just wanted to mention that today is the 10th anniversary of Giving Day, a wonderful Santa Cruz tradition that has raised millions of dollars through thousands of small donors for student programs and activities on campus. We have QR codes on the tables over here for those of you who are here in person, and those of you online, we will be sending you a link. Now I'll turn the program over to Professor Leauthaud.
Thank you. It's really an honor to be able to introduce Professor Alexie Leauthaud. Alexie did her PhD in France at the Laboratoire d'Astrophysique in Marseille. Then she was a Chamberlain Fellow at Lawrence Berkeley National Lab, followed by a Distinguished Fellow and faculty at the Kavli Institute for the Physics and Mathematics of the Universe in Tokyo, Japan, before we then brought her back to California as a faculty member at UCSC. So Alexie has won numerous awards, including the Packard Fellowship, the Sloan Fellowship, the DOE Early Career Award. Her astrophysics research tackles the big questions in terms of like the nature of our universe, so cosmology and galaxy evolution. She's the spokesperson of the DESI survey, which just this year had truly groundbreaking results indicating that potentially dark energy is actually evolving in time. So that's really a potentially fundamental shift in the way we see the evolution of our universe and what it's made of. And, you know, if that work wasn't enough, then Alexie also spends a lot of time thinking about sustainability and climate change. And so she has numerous programs in that as well. She's a founding member of the UCSC Climate Action Now. She convened Council of Deans and academic leaders to discuss how to make academia itself, so higher education, more climate friendly, and how we can tackle climate change in our universities. And some of that work has led to now a 100-page paper that is in preparation. So we're really fortunate that Alexie is both working in both of these areas of both understanding our universe and then also and our place in the universe, and then how we can really also tackle the issues that we have here at home. I am personally incredibly fortunate that Alexie is one of my collaborators, and so I get to work with her on science, which is just amazing for me. So please.
Mic check. Good. I would like to dedicate this lecture to Jane Goodall, who was an amazing scientist and an inspiration for women, just an overall outstanding scientist, and whose message about conservation and preserving life on our planet, I hope she would endorse in the second half of this lecture. So when I was a wee one, I was inspired by books by Carl Sagan, in particular, The Pale Blue Dot. I think many astrophysicists today were inspired by books such as Carl Sagan. But when I was a wee one, I looked at this book and I looked beyond to the stars and I thought, wow, you know, the universe, amazing. I'd like to go and study that. But as I've become more mature, maybe wiser, I don't know, I'm looking back to the Earth and thinking that preserving the habitability of our planet is the first and foremost thing that we need to do. So this is the journey of my evolution. But let's start with the universe. So we're going to go through the history of the universe in about 30 seconds. So the universe began, that was the wrong one. The universe began, 13 billion years ago in what's known as the Big Bang. out here. In the very, very early phase of the universe, there was a huge expansion driven by quantum fluctuations. It's called inflation. The universe expanded many times over and grew extremely large. Out here, you have the formation of the first stars and the first planets. Out here, the formation of the solar system. And then at late times, the second half of the expansion of the universe, you see accelerated expansion, which is related to dark energy, and that's going to be the first part of my talk. So we're going to talk about the accelerated expansion, and then out here we have Earth, which will be the third part of the talk. In physics and astronomy, nothing is more true than the more we learn, the more we realize how little we know. And the more you progress in your scientific career, the more you realize how fundamental and true that is. This is especially true in the field of astrophysics, where we have come to understand that regular matter only makes 5% of the universe. So regular matter is this chair, it's the carbon and the oxygen that's in your bodies, it's the water that you drink. That's all regular stuff. For an astrophysicist, that's not too interesting. But it's all that we know. Everything you've touched, everything you've ever known is regular matter. A whopping 26% of the universe is made up of dark matter, an unknown substance that we'll talk about in the second part of this talk. And then an even more whopping, about 70%, is in the form of dark energy. So most of the universe we don't understand. So my talk will be divided into 3 parts. We'll talk about dark energy, dark matter, and then we'll follow that zoom back towards planet Earth, and we'll talk about the big picture challenges facing continued life on this planet. So let's start with dark energy. And I want to try to distinguish dark energy from dark matter, because they're very different things, and yet they have similar names, maybe just our lack of creativity in naming them. But dark energy, as the name implies, is a form of energy. It is 70% of the mass plus energy budget of our universe. The main impact it has is to take the expansion of the universe and accelerate it at late times. So the universe is expanding, and since the last about 7 billion years, that expansion has been accelerating due to this effect of dark energy, which has a negative pressure. It earned a Nobel Prize in 2011, and we have few theoretical compelling ideas to explain dark energy. So studying dark energy is really observation-driven. We're studying it through telescopes, but theorists are quite stumped as to how to explain dark energy. Dark matter is a very different story. Dark matter, as the name implies, is a kind of thing. We think it's a kind of particle, but a particle that we haven't yet detected. So it's more similar to the chair than is dark energy. It represents 30% of the mass plus energy today. It has been unambiguously detected in astrophysical observations. There's no questions as to the existence of dark matter. It earned a Nobel Prize in 2019. With a little side note, I will note that it's well known that the Nobel Prize is fairly gender biased, and many think that it should have been awarded to Vera Rubin for her discoveries on dark matter. We have been searching for this for 30 plus years and yet have discovered nothing concrete. We can't say that we've ever captured a dark matter particle. So I'm going to start with dark energy, and I want to tell you about results from the Dark Energy Spectroscopic Instrument. And as Tesla mentioned, I'm honored to serve as the co-spokesperson for DESI, which means that I'm responsible for the scientific coordination and scientific output of this collaboration. This is a team of 900 scientists that are using a telescope, the Mile telescope, at Kitt Peak in Arizona. And we are studying the expansion of the universe by measuring the distances to galaxies. So in this video that I'm going to show you, each of these points is a real galaxy that has been measured with this telescope from Arizona. So here we're zooming through a real video, but that's also artificially generated because we can't zoom through the universe. But each of these galaxies is a real galaxy that has been observed, and you can see how they congregate in structure. They're not uniformly distributed. They have a structure that's called the large-scale structure. And I'm not going to talk about the specifics of how we get from here to dark energy. I have a backup slide if you want to ask me about it, but we'll skip straight to the dark energy results. And I'm going to sort of tell you why these results generated so much interest. So these results were highlighted, maybe a bit of a dubious distinction, in Time magazine. We were cited right next to the page that talked about AI application of your eyelashes. But my colleagues, I'm not sure well, anyway. So we were also cited across newslets across the world in more than 20 languages. These are the two papers that came out in 2024 and 2025. If you are a scientist, you'll look at the citations, you'll understand that this is an incredibly high citation rate, demonstrating the interest in these results. This instrument was also designated University of California Top 12 Inventions for 2024 and earned a prize from the Astronomical Society this year. Okay, so what is the result? Astrophysicists believe that we have a model for the universe that's called the Lambda cold dark matter model, also known as Lambda CDM. And in this model, we have dark matter and dark energy and a few other ingredients, such as general relativity. And this model does a phenomenal job at actually explaining many things in the universe. So it's the cornerstone of our understanding of the universe today. But in this model, the dark energy parameter is thought to be a constant. These are what are called the Einstein field equations. They describe the laws of general relativity that bind our universe together. And on the left here, this is the geometry of space-time. On the right here, this is the mass and energy content of the universe. So one way to read this equation is to say that space-time on the left, sorry, the pointer is a little hard to operate, and space-time dictates mass plus energy, and mass plus energy dictates how space-time curves. So that's our fundamental understanding of the universe, but DESI's new results suggest that this lambda parameter, which is the dark energy parameter, may not be a constant. A profound implication of this is that they may have to repaint this wall. So this is one diagram from that most recent paper. This is time along here, so this is today, going out to 10 billion years ago. And then on the y-axis, this is a parameter that dictates the behavior of dark energy. So the first result that sort of leads to this paradigm shift is that a constant dark energy would be this line. And what you're seeing is that the blue curve clearly isn't a straight line. So the first finding is that the recent results tentatively suggest that dark energy changes with time. The second result is that if you ask theorists what their expectation would have been before the results, after the results, of course, everyone has a new theory. But before the results, everyone would have thought that dark energy would be up here in this quadrant, which is a regime called quintessence. These are quintessence models. However, the second surprise from these results is that this blue line, especially at earlier times in the universe, lies below here in a regime that was highly unexpected. So this now has given theorists a lot to work with, and they're extremely happy, and now they're playing around with new models for how dark energy might behave. What does this mean for the future of the universe? This is the Big Bang today. This is the present time, so we've gone through this accelerated phase. And there are various future possible scenarios. One is the Big Rip, where the universe expands to such a degree that matter itself is ripped apart. The second is a Big Crunch, where the universe recollapses on itself, maybe forms a new Big Bang. And with the dark energy model that we've had before, we kind of thought we were in this middle scenario. So you're going to ask me, where do we think we might be now? And I'm going to tell you, we still don't know. Because the truth is, to predict the future, you have to have a physical understanding of dark energy, which we don't. So, but we do know that the recent results suggest that dark energy might be weakening. So acceleration may be slowing down, suggesting we may be somewhere in between this curve and the Big Crunch. We could still go to a Big Crunch. It all depends on the physics of dark energy. I'll now move on to dark matter. So remember, dark matter is a thing. It's a particle. We've been looking for it for 30 years. So what is dark matter as opposed to dark energy? It is thought to be a real particle, something like an electron or a neutron or a proton, except that it has other properties. One of the main properties being that it does not interact with light. So in theory, there are billions of dark matter particles streaming through this room, streaming through your body, but they don't interact with your body, so you're kind of like a glass to dark matter. It just goes right through. There are lots and lots of different ideas about what dark matter might be. So unlike dark energy, for which we have few theories, we have lots of ideas about what dark matter might be and lots of different candidates. How are we looking for dark matter? There are two ways in which we look for dark matter. One is from the Earth. We build detectors. So this is an example of a recent experiment that's actually looking for dark matter. In this scenario, these would be dark matter particles that once every so often interact with regular matter and leave a detectable signal. But dark matter might not behave that way. So it's not guaranteed that one would find a detection with these ground-based experiments. This is based in an underground mine in South Dakota, buried 1.5 kilometers underground to avoid interference with other particles. The second way that we look for dark matter is with astronomical observations. And one of my lines of work specializes in searching for dark matter with telescopes. I'm showing here the recent Vera Rubin Observatory that saw first light recently, one of our newest, largest telescopes in Chile, in the Atacama Desert. And so this facility is going to be, one of its key goals will be hunting for dark matter. I want to briefly mention a program. I created this program with a colleague of mine from Princeton. It's called the Marian Program. We named it after 17th century Maria Silvia Marian, who was the first female entomologist. She studied tiny little insects, and we're studying tiny little galaxies, so we thought that would be appropriate. So we are studying what's known as dwarf galaxies, tiny, tiny, tiny little galaxies, such as the ones shown here. So these are called dwarf galaxies. And dwarf galaxies are thought to be excellent places to try to understand dark matter because we think that they contain a lot of dark matter. So from an astrophysical perspective, this is a good place to be searching. We built two very specialized filters. These are the same filters that would go in your camera if you wanted to get a red or a green or a blue image, except that these ones cost $100,000 each. And we put them on this Blanco telescope in Chile, and we've been, we spent 60 nights observing the night sky for this program using these specialized filters. I don't have as exciting as results as DESI to show. This is still work in progress, but I want to show you these two students and these two little galaxies that we've observed from our program. And over here, I'm not going to tell you about the technique that we use. I do have a backup slide if you want to hear about it. It's called gravitational lensing. But we're looking at the dark matter amplitude around these dwarf galaxies. And what you're looking at is all these blue points are above 0. So there's a clear detection of dark matter. And this is a scale. So this is going outward from the galaxy. So we have a very clear, highly significant detection of dark matter around these dwarf galaxies. And this work is ongoing, led by a former student and a current student, Zhao, who works with Tesla. So I'm going to move on to the third part of my talk, which is now zooming in to talk about life on our planet. So in 1990, the same Carl Sagan that we talked about in the beginning of this lecture asked Voyager 1 to turn around in its outward journey into space and take a picture of Earth. And this image became iconic, and this is the pale blue dot that gives the name to the book. And so this is our Earth here as seen from outer space. Now, in our short lifetimes, it's very tempting to assume that human life will continue into the vast future. But from the cosmic perspective, remember this lecture we're going to talk about cosmic time and cosmic distance scales. Nothing is less guaranteed. In fact, Earth has witnessed 5 major extinctions, and 98% of life on Earth has already gone extinct. So we're going to talk about the short and the long-term challenges facing human and non-human life on Earth. I want to start with cosmic time. We need to think about time scales and length scales to understand the scope of some of these problems. This is yet another Carl Sagan invention called the cosmic calendar, which I absolutely adore. This is putting the entire history of the universe onto a 1-year timescale to make it more understandable to us. So the Big Bang starts on January 1st. And then in September, you have to wait all the way until September to get the formation of the solar system. And then on December 24th, so Christmas Eve, you have the formation of Pangaea, the supercontinent. That'll actually become relevant in a little bit. And Christmas Day, dinosaurs. And then the final day, well, the 30th, dinosaurs go extinct because of the asteroid impact, which leaves an ecological niche for mammals to take over. And then over here, we're starting to have Christmas dinner, humans and chimpanzees split. And then the final minute, all of human modern history is within the last 45 seconds. All of written records is in the last 10 seconds. And your life is a fraction of a second on this cosmic timescale. So this is why I say we shouldn't just assume that the things that happen over our lifetimes are going to continue into the cosmic future. So Earth is a vast oasis for life, but I want to show you it's surrounded by a vast emptiness that we're going to demonstrate for you. So I'm going to ask our sun, Tesla the star, to stand up. So Tesla is our star. And we're going to walk, so this is going to be a scaled version of the solar system, which we're going to have to use a bit of creativity because this room isn't big enough. But we're going to walk 10 steps over here to get to Mercury. Andrew, you're going to be Mercury. So Mercury is this tiny little bead. Okay, now the first thing you might want to notice is that we often think that Mercury is scorching hot right next to the sun. It's so close, it's burning out. Yeah, it is hot and scorching, but it's this tiny little bead all the way over here. Okay, so now we're going to take an 8 steps, which is going to bring us back over here. What's our next planet? So you are Venus. And now we take 7 steps. And my steps are a little bit, they're too small. They should be a bit bigger. Kevin is going to be Earth. So Earth here, I want to just show you for a second. This is the Earth and this is the Moon. So the first thing I'd like you to think about in this cosmic distance, this is the distance that humans have traveled so far. There are people who talk about colonizing Mars, which we'll talk about next. Mars is 14 steps. 4, 5, 6, 7, 8, 9. We're going to have to go back again. Kind of ruins the demo, but anyway. So think about this distance. Now we are at Mars. This is the distance that's required to get to Mars. That's the distance that we've traveled so far. Secondly, unfortunately for us, in our solar system, neither Mars nor Venus are actually habitable. So we can put those cards down. I'll just hold on to this one. Thank you. You can hold on to those cards. Thank you. So the point here I wanted to emphasize is to give you a real understanding of the distance scales in the universe and how our planet is isolated. We're not going anywhere else. So humans will not move to Mars, despite things you might read in the media. We will visit Mars. I do think that is achievable technologically. We can visit Mars, and that will be a fantastic achievement. But we need to distinguish the difference between visiting Mars and moving to Mars. Okay, given that distance, the energy resources to move to Mars would be impossible. And there's a difference between moving all of humanity and life to Mars versus having a few people live there. Furthermore, from the point of view of physics, making Mars habitable just isn't possible for many reasons, but the main reason is because it doesn't have a magnetic field. And the lack of magnetic field means that it is unable to sustain a thick atmosphere, which would protect us from harmful cosmic rays. And we do not have the technology, I don't think we will ever have the technology, to get the core of a planet to churn to recreate a magnetic field. So that was to say that we have one finite planet. That is the situation in which we are, and I hope I've demonstrated that for you. So we don't have a second chance. Unfortunately, we are in a circumstance now where we are over-consuming the resources of this planet. So the second part of my talk is about trying to think about becoming a planetary species that understands its planetary boundaries. We are currently what's called Earth overshoot, meaning that we use up more resources than the Earth can generate. In America, we use up about 5.1 Earths per year, meaning that we use 5 times more than the Earth produces. You're going to ask, well, how is that sustainable? It's a bit like deficit spending, where our bank account is going negative, and that's not going to be sustainable. So if we want to consider humans on long time scales, other life on long time scales, we need to become a civilization that recognizes these planetary boundaries and operates within these planetary boundaries. Continued growth on a finite planet just isn't possible. So some of the Earth systems that we need to be thinking about from a large perspective are the atmosphere, the ocean, the ice sheets, the fresh water, and the biodiversity. And we need a fundamental shift in the way we think, because it used to be that when we ran out of resources, we'd invade our neighbor. Or we'd get on a boat and look for a new island. But that's not possible on scales beyond the Earth. There is no other island that we can hop to. There really is no plan B, okay? Now, I want to give you an astronomical example of how large the impact of humans on our planet currently is. You've heard of climate change, we'll talk about that in a minute, but humans moving water around for irrigation and climate change leading to the melting of the ice sheets has now had a noticeable impact on the wobble of the Earth that has been detected. So we have changed the wobble of our own planet. This is a whole new era. We are impacting the planet on large scales. So these are planetary boundaries. They were determined by the Stockholm Center for Resilience. There are different ways about thinking some of the zones that we shouldn't transgress. So some of them are, we want to keep our oceans healthy. We don't want our oceans to be acidic. We want to make sure we don't change the flows of phosphorus and nitrogen too much. We want to keep fresh water. We don't want to entirely change the way that lands are used. We want some wild spaces. So there are these many different safe zones that we should be operating under, and we're currently not operating under them. According to these estimates, we've already crossed 6 of these now 9 planetary boundaries. This is also related, obviously it's complicated, but also related to the growth in our population, going from 1.5 billion in 1900 to 8 billion today. I would encourage everyone to watch this movie. I watched it with my kids, A Life on Our Planet by David Attenborough. This is a brilliant movie because it is a personal testimony from David Attenborough as to the changes he's witnessed in biodiversity and on the planet over the course of his lifetime, which is a fraction of a second of cosmic time. Now, I'm going to focus today on climate change because I believe it is our most pending threat, but it is not the only one. There are many planetary boundaries, and then I'll talk also about future threats. We really need to think of it as one threat among many. The most urgent threat to life on Earth are climate and the biodiversity crisis. These are related, the climate crisis is related to us putting too much CO2 into the atmosphere and fundamentally changing the balance of our Earth system. So this is time over here, this is today over here, this is about 1 million years in the past. This is carbon dioxide levels, and carbon dioxide levels have varied over time, and they have often correlate with changes in temperature, and in fact, many past extinctions have been related to varying levels of CO2 changing the Earth's temperature. This is today. This is the Holocene, the last 11,000 years of our history. We have benefited from 11,000 years of a very, very stable climate called the Holocene, under which all of modern human history has evolved. So this is this little zone here. These are the carbon levels today. So what I want you to notice is that the carbon levels are much higher than anywhere in the past over 1 million years of Earth's history. Earth's system is already out of balance. What are the consequences? One of the things that I read about that really caused me to stop and understand the impacts of this was a study by Lenton et al. In 2022. And so I'm going to share this with you now. And this is the thing that keeps me awake at night. But this, I think, really might help demonstrate the impact of the changes that we're talking about. Lenton defined the human climate niche, which is the temperature ranges in which we are comfortable living. You know, at some point it becomes too hot and we just can't sustain living and air conditioning, and it's just too hot to even go outside. So currently we are on a trajectory to get to about 3 degrees of excess warming above current temperatures. The estimate is that if we hit this degree of planetary warming, more than 1 billion people would be forced to migrate away from the equators. So I'm just going to pause and let you read that number and digest that number. And that would be predicted to happen within the next 70 years, if we continue on our current trajectory. And then, in addition to the human crisis, I want you to think about the geopolitical tipping points that might cause. There are other consequences which you also are familiar with. One is rising sea levels. These are the ice sheets on Greenland. Those are currently melting. Those were formed by millions and millions of years of snow accumulating on the ice sheets and not melting. So it created these giant sheets of ice which are currently melting. We don't have the technology to put all that snow back on Greenland or in Antarctica. So that is one of the reasons why sea level would be rising. This is a predicted picture of Miami with a temperature rise of 2 degrees, which is our current trajectory. There are other tipping points, which I don't have time to go in today, but there is a nice paper here about many other consequences of changing our atmosphere in such a drastic way. Some are losing the Amazon rainforest, losing the coral reefs, and these are the melting of the ice sheets. Also potentially changing this ocean circulation, which impacts the climate of the east coast of the US and of Europe. So I moved to Japan in 2011. I was there as a faculty for about 5 years. I moved there shortly after the earthquake, only a few months after that dramatic earthquake. This is an image of the tsunami coming over the seawalls. And I mention this because I want to emphasize that techno-optimism can be fatal. And it was fatal for the Japanese living in this area. Historically, the Japanese have stones in the mountains that go many, many hundreds of years in the past. And it was known that if you had an earthquake, you would go up the mountain to the stones and you would be safe. But this didn't happen because there was, confidence in these seawalls, that the seawalls would protect you from the tsunami. Techno-optimism applies to the climate crisis as well. And I want you to think of this image when people talk about climate solutions. I want you to think hard about whether they are genuine solutions or whether they are Band-Aids that we're fooling ourselves that's going to fix the problem. So here are some of my techno-optimistic fairy tales. So I'm going to call this technology, the idea that technology alone is going to get us out of this fix. Assuming that we can suck huge amounts of carbon dioxide out of the air, we can do a little tiny bit, but we really can't do it at scale. Assuming that artificial intelligence is going to solve the climate crisis, this isn't going to work for many reasons, but the climate crisis is not just a technical problem, it is also a social and a political problem. Assuming that a future technology is going to solve the problem, assuming that deploying wind and solar is going to allow us to continue current lifestyles, assuming that if you go out and buy an EV, then you've done your part. These are all techno-optimistic fairy tales that justify our current lifestyles. It's like my kids when they tell me, "Mom, I'm eating vegetables." Oh, and this is tomatoes, so that's good. And this is parsley, so here's some greenwashing throwing into it. Right? It's the same thing. We need to understand that these are fairy tales and talk about real solutions. The inconvenient truth that we don't talk about enough is that we need urgent and extremely profound changes to the ways in which we live, to the ways we distribute wealth and collaborate internationally. We need to be thinking about much more modest lifestyles. And the best analogy I could come up with is we need to be more like bees. We need to be thinking collectively as the collective good on planetary scales, and less about my individual needs or the needs of my country fighting for resources. We don't have that luxury anymore. We need to come together as a planetary level species. And quite frankly, my job as an astrophysicist solving dark energy is a much easier problem. So this is an article from the New York Times from a few years ago called All Hands on Deck. It talked about how astrophysicists seem to be at the forefront of a movement of scientists coming back to look at Earth and thinking, this is really urgent. We need to be working on this. This is an observatory in Australia called the Stromlo Observatory, which was burnt down in 2003. This is the DESI telescope, which we work with over here in Arizona, which almost burnt down in 2022. These things are having real impacts, not only on our lives and your lives, but on our professions. And in the current trajectory towards 3 degrees, we're not going to be building telescopes. We're not going to be spending lots of money on expensive Rubin-like telescopes. So we need to understand that there will be no luxuries at 3 degrees unless we take action now. There are climate solutions at this point, all of which need to be deployed. So I want to encourage you, and in fact, I have this handout here, which will be at that table over there if you want to take it. I've got various links from the talk and QR codes, including the link to Project Drawdown, if you want to take that home with you. It has a fantastic explorer here, where you can click on various different climate solutions and understand their impact. So unlike some of the other ones that we talked about, these are quantified, they have numbers, and you can look at which ones are more impactful or less impactful. So I really like this viewer, and I highly recommend going and looking at it. But missing from the conversation is often the piece about lifestyle change, which we do not like to talk about. Carbon emissions per capita, the US is way out there in terms of carbon emissions, 50 tons per year per person, compared to, for example, someone from Kenya, 0.4 tons. So we bear a very large burden in terms of the creation of this problem. We also bear a large burden in terms of fixing this problem, and we're going to need lifestyle changes. So some of my work is now moving towards planetary sustainability. The topics that I've been thinking about are in this drawdown project. They're related to improving diets, reducing food waste, increasing composting, and things like this. So these are solutions that we can all work on. And I brought this book today because I think this is a rare book that has a lot of really practical examples about how to change things within suburbs. Most people in the US live in suburbs now, and this book has a lot of really interesting ideas. So I've linked this in the handout, and I've got this book if you want to come and browse through it. Okay, so some of the things I've been thinking about are what I'm calling ultra-local food production. So encouraging people to grow more of their own food because it's fun, because it's healthy. It's so great to get kids involved. And I'll show you why there are additional benefits. So these are some garden beds that we've built on campus. These are 8 feet by 4 feet. They're about a good size for an urban garden. And then student Liliana has calculated for Santa Cruz, LA, Santa Clara, how many garden beds you can fit within residential lots. So these are real residential lots. And here you can fit 2, 3, 4, 5, 6, 7 garden beds. Where are we going with this? The idea that we don't need to be watering lawns. We could be watering food, and also we can be composting. So these are preliminary findings from Liliana, is that Santa Cruz and LA have significant space for home gardens. And there's a new California law, SB 1383, which actually requires municipalities to send all organic waste to the landfill. That's a good thing because the idea to composting, that's a good thing because the idea is we're trying to keep this organic waste out of landfills where they generate methane, which is an even more potent gas than CO2. So we're trying to prevent that methane from happening. But the idea that we are working with is, there's billions of dollars going to be spent on building new composting facilities. What if we took some of that money and gave it back to the people to help you improve your home gardens and do your own composting in situ? And she's calculated that doing that, so you're preventing all this waste from going out to a commercial facility, is about $20 million annual savings for Los Angeles. So take that $20 million, give it to the people, and encourage composting and growing food. There are additional, probably larger savings from health costs due to toxic chemicals that come out when you compost on a very large scale that Lily is currently calculating. My personal hunch, based on my own sort of experience, is that Santa Cruz, Santa Clara, and LA could probably grow all of your greens locally. And that's probably an underestimate because I've seen examples of what are called micro farms. These are very intensive urban gardens. And I've got some links from you here. This is an example from the Plummery. It's a micro farm in Melbourne. Very tiny area. Many of you probably have much larger lots, producing 900 pounds of food year-round, and composting and all of that. Here's another example from Los Angeles, another micro farm, and there are several in the Los Angeles area. Other sort of sustainable work that I've been working on is rainwater harvesting, because we need to preserve fresh water. So we're working on designs that will take rainwater and then irrigate your food so that you're growing your greens, but also irrigating them with rainwater. We found that we've chosen this tank size, 500 gallons, because it represents a good compromise between size and price. It's about $1,000 to install one of those. You can do it yourself. We have videos. And this can fully irrigate 2 beds. And we get no rain in this area from March to October. You can grow 600 lettuces in 6 months with no rains using one of these tanks, which is more lettuces than one person can eat. We're also working on composting because part of the idea in the previous slide was that the savings come from preventing organic waste being trucked around to distant facilities. So then you would compost to grow your own garden. So we're working on cheap, DIY, rat-proof systems for compost. I will say we have a lot of videos here. This is still young. We're still working on it. We have failed yet to build a rat-proof composting system. I have videos of them getting into our systems. So we're still working on that, but stay tuned. We have some good ideas. Why would you do this? It's good for the planet. It's also good for you. We've worked with local families in Santa Cruz, especially working with their children to deploy gardens and look at the impact on their children. So we've been building these children's gardens. And these are quotes from our study about how these children have gone from not liking vegetables to liking vegetables. So I'm just going to quote. These are genuine quotes. Alyssa is able to identify different plants, pick out what he likes, and rather than just greens is yucky. Alberto has changed his stance on I don't like lettuce, so I can eat it every day. So there are real, and one of the, one of the big things that comes up when you look at these climate changes is improving diet, in particular reducing meat and eating more vegetables. And so this is a very practical way at home to improve your diet. It's delicious, it's organic, you've grown it yourself, it's a lot of fun. So coming back to the big picture, if we want to transition to be a planetary level species that will endure in cosmic time, not just in a fraction of a second, my main message for you all is that we all need to act now. You can't be relying on the technology. You can't be assuming that the big companies are going to solve this or that politicians are going to solve this. It's much more complicated. You could work on some of the things that we've been working on. If you're interested, we have videos and some QR codes. But there are many other things. You may have different interests. I encourage you to look at Project Drawdown or this Project Shift, which can give you different pointers depending on your personality and your looks and wants. So looking forward, we're going to step back and take another big step backwards to look in cosmic time. It's obviously hard to make predictions about the future, but let's see what we can do. Let's imagine that we have come together as a planetary species and solved the current climate and biodiversity crisis. What are the future challenges for sustained life on Earth? There's nuclear war, which could happen at any time. I'm putting a level of severity over here. So there's going to be difficult, and then there's going to be fatal. Nuclear war is difficult, but probably not fatal. Bioweapons or disease, we had the unfortunate experience of this in 2020, could happen at any time, difficult. We will run out of resources. I'm highlighting one example. The resource depletion is phosphorus. Phosphorus is one of the key ingredients in agriculture. It's one of the reasons we have high yields, because we use our phosphorus resources, which are currently predicted to run out in a few hundred years because we use it very wastefully. This is difficult, probably not insurmountable. We'll just have to deal with less food and be more careful. Supervolcanoes happen on tens of thousands of years time scale. We have supervolcanoes in the US. There have been supervolcanoes in the past, and this hasn't generally led to an extinction. So this is unpleasant and difficult, but not extinction level. Asteroids. This connects back with our work as astrophysicists, because our colleagues map out asteroids. Some of our colleagues work with the military to identify asteroids and identify those risks. These happen on millions of years timescale for a kilometer-sized asteroid of the kind that wiped out the dinosaurs. This would be fatal depending on the size of the impact. So small impact, not so fatal. Larger impact, fatal. And a very large impact would be catastrophic. The formation of the next supercontinent. 250 million years ago, we had the supercontinent called Pangaea, which coincided with one of the largest mass extinctions in Earth history, called the Great Dying. Another 200 million years in the future, there is expected to be the formation of a new supercontinent, Pangaea 2. And the formation of the supercontinent will lead to large amounts of volcanism, large amounts of CO2 in the air, and potentially reduction of ocean circulation. All of these things are going to make it very difficult to live in this era. The good news is that if we have solved climate change and we are able to do some level of planetary controlling of the atmosphere, maybe 200 million years from now, we can throw a bit of techno-optimism into there. A nearby star could explode. These could happen on millions to billions of years time scale. Depending on the distance of that star, it could be fatal. So the star exploding will emit a large amount of gamma rays. If it's far away, it'll have a minor impact. It might have a minor impact on cloud formation or mutation levels. But if the star is too close, then it would have a very severe impact on our ozone layer and would induce genetic mutations. So potentially fatal. This is going to be a big challenge if we're around billions of years from now, would be the loss of our magnetic field and the loss of our atmosphere. Good luck engineering our way out of that one. Another challenge, 5 billion years from now, our sun will change its state. It's going to start burning helium, and it's going to expand, and it's going to become a red giant. The outer envelope of the sun will engulf the planet Earth. So if we're around billions of years from now, there may be solutions. I'm just speculating, but maybe we would move to one of the moons of Saturn or Jupiter. And then finally, there's an utterly fatal end, which I'm going to leave you as a cliffhanger in case you want to ask me questions about it. But there is a physical idea called vacuum decay, in which the universe would transition from one state to another. Again, I'm not going to go into details, leave it as a cliffhanger. But at the speed of light, particles would cease to exist, and this bubble would expand at the speed of light, and we would instantaneously disappear. And there's no technological solution for that one. So I'm going to wrap up. I want to talk for 1 minute about the colonial myth of the endless frontier. We need to recognize in our psyche that we have lived through an era of colonialism, in which when we ran out of resources, we invaded our neighbor or we went to another island. That's not going to be possible moving forward. And I'm going to quote from these papers here, just as not all civilizations on Earth engage in colonization and extraction economies, neither might intelligent extraterrestrials. We assume in our field that we have colleagues who look for aliens through programs like SETI. We assume that extraterrestrials are busy emitting energy and sending probes and coming to visit us. But the greatest sign of intelligence might actually be a species that preserves and cultivates its planet and has a low footprint. It's not sending all kinds of energy out into the universe, rather than recklessly consumes and exploits endless worlds. So this is what I really need to think that we talk about, is preserving and cultivating our planet and dropping this myth of the Star Trek going out and expanding and colonizing. I do believe we can come together as this planetary species, but to do so, we need a vision like this one. We need societies in which wealth is shared across countries and peoples. We're not going to be able to solve the climate crisis or the biodiversity crisis when we have huge wealth inequities. We need resources that are used wisely in moderation. We need to transition to modest but happy lifestyles where local economies are prioritized, planetary health and all life forms are respected, and growth is limited. And by growth, I mean all kinds of growth, population growth, economic growth. So I will conclude here, and I hope you take away that continued life, human and non-human, is far from guaranteed on cosmic timescales, and your creativity and ingenuity will be necessary for us to face these cosmic odds. Thank you very much.
So now we're going to take questions. I think we come over here. So I'm gonna take my purview as moderator and just start us off with a question. So as someone in higher education, I know you've worked on this as well.
Right.
What can we do at our universities and as instructors in higher education?
Yes, I think there's lots we can do. We have very privileged positions as educators. I think we can expand teachings on climate and biodiversity and big picture questions such as these. So there's a teaching aspect that I think we can expand. But beyond that, there's a much more difficult question, which is that in science and education and higher education, we have become ultra specialized. So many scientists are extremely specialized in these deep silos of knowledge, but the kind of problems that we need to tackle are high-level, interdisciplinary, very complex problems, and we're actually really not trained for that. So we need to think about encouraging more knowledge and research on high-level, big questions that will tackle sort of beyond our boundaries of astrophysics or biology or social studies, right?
Okay, please. There's a microphone coming.
Hello. I serve on the Santa Clara Valley's Valley Waters Environmental and Water Resources Committee. And for those people who live in Santa Clara Valley, in County Santa Clara, they have access to two things. There's access to something, to rebates if you remove grass from your lawns. Replace with something environmentally friendly, you can get rebates from the county. Secondly, you can get rebates for water barrels like you proposed. So I'd like everybody to take advantage of these programs, Santa Clara Valley Water. Thank you.
Thank you. That is fantastic. Those are fantastic opportunities. I encourage everyone to take advantage of it. I will say that in Santa Cruz, my own district, there's no rebates for rain barrels. So that is a policy question that we'd like to advance in Santa Cruz.
Yeah, we do have the grass removal because our HOA is talking about that. Actually, we're going to remove.
We
some
do
grass.
some things, right?
Yeah. Well, okay.
So yeah, I want to go right to the HOA question. If I do that in my community, I'll get fined. I think it's correct that I have neighbors that you wouldn't believe how big these yards are. They're like 2 acres, and they have to water 2 acres 5 times a week, keep it green, and cut it, and have the clippings removed and thrown. But if we don't do that, they fine us. And somewhere along the line, somebody has to step in and say that the HOAs can't require you to do that. Because right now, I have to keep my lawn green. I would prefer that I not have to water it for no reason and have a minimum yard, but there's just no way to do it. Is there any way that we could get something passed that says the HOAs just cannot force you to water your grass? Year-round, okay? And these things are being watered like, they're watered sometimes during the day. and you're going, people just do it because they're scared of the HOA.
I think those would be excellent policies. And on the large yards, there's a famous urban gardener from Canada who became famous on YouTube because he was going around, he went to people and said, I'm going to cultivate your yard, and I'll grow stuff, and I'll give some produce to you, and I'll take some, and I'll sell the rest. And he had multiple houses that he was working that way, and I thought that was a really interesting hybrid model. Yeah.
Yeah, that's an interesting point that I hadn't considered. We do have actually a number of people on Zoom watching remotely, so I want to see if we can take some questions from online.
Well, yeah, we can. So far, there's no open questions in the Q&A, so everyone on Zoom, you are encouraged to ask questions. In the meantime, I think we can go on with the room, unless...
Sounds good.
So on a different part of the subject, and speaking in terms of cosmic time, I guess, how close are we, or you perhaps, and the people you work with doing research on the dark energy, how close are you counting yourself as being on your way to figuring it out?
I wish I could say tomorrow, then I'd go to Stockholm. But the answer is, I don't know. Yeah. We have lots of hints in the data. There are extra experiments being planned that will continue to map this out. So after DESI, we're actually currently working on the next generation called DESI 2. There's the Rubin experiment that Tesla works with. So we're going to get huge amounts of data to try to tease out what dark energy is doing. That needs to be combined with the theoretical insights from our theoretical physicist colleagues about what it could be. But we could be a few years away, we could be decades away.
Or hundreds of years away.
There may be some, my fear, and actually I just wrote a piece in Nature about this, is that there may be problems that are just too complex for us to solve. So dark energy, we've been assuming, is this simple lambda, a very simple model that's constant. But there are models out there in which dark energy interacts with dark matter or interacts with gravity. And there's nothing to say that the universe is simple. So it could be extremely complicated, and it may be too complicated for us to figure out. I don't know. So anywhere from a few years to decades or never.
Well, if I could be slightly more optimistic. Well, okay.
She's
so,
optimistic.
for example, dark matter. We still don't know what dark matter is,
Yes.
and we've been working on it for, well, if you go back to Zwicky, close to 100 years.
Yes.
But we have learned so much. Like, we can't, pinpoint this is it, but the theories that you can come up with for,
Yes.
what it might be are incredibly constrained, right?
Yes.
We know a whole lot about it.
But what if dark matter interacts with dark energy?
Well, it could reveal itself, yeah.
That would be a lot more complicated.
Yeah.
And what if there are multiple forms of dark matter?
Yeah, that is a big one that now people are starting to think more seriously about. Yeah.
So we always have assumed in our very simplistic models that there's one kind of dark matter, but there might be 5 of them.
A lot of kinds of matter.
There's a lot of kinds of regular matter. Why not many? And if there's many kinds of dark matter interacting with dark energy, we're going to need some really clever children to figure that out.
It's all up to you, young man.
That's correct.
So I have a question.
How about we take a question and then we'll come to you?
Can you hear me? Okay. Continuing to ask about dark energy, in one of your slides of cosmic expansion, you showed a deceleration stage followed by an acceleration stage, presumably due to dark energy.
Yes.
Do we understand what happened with dark energy in that phase?
So the universe expanded through the effects of the Big Bang. So it was still carrying that energy from the Big Bang. Started decelerating, but about 7 billion years ago, so half of the age of the universe, the dark energy started to take over and then drove the expansion. Now, it depends on the physical model for dark energy. The most simple form of dark energy would be that dark energy is associated with empty space. So it's an energy of empty space. The odd thing about this is that as the universe expands, it creates more space. Mm-hmm. And as it creates more space, it creates more dark energy. which then has a
So that's the
negative pressure.
accelerant. That's the
And
accelerant. Okay.
then it accelerates. So it's creating more dark energy as it accelerates. But that is one model for dark energy that seems to be ruled out by the current data. To be able to say something more concrete about physically what that happened, you'd have to have a model for what it is. Some people believe that there's a connection between dark energy and the early period of inflation. Inflation in the very, microseconds age of the universe was a period of incredible expansion, not unlike acceleration. So maybe there's physics that connects early inflation and dark energy. Maybe there are multiple things going on and there are other parts in the history where it's accelerated a bit and we haven't noticed. So
Yeah, I mean, one thing is that if we lived in a different part of history, we might not know dark energy was there at all, right?
Right, right.
Yeah.
So I was dismayed to see that you don't think that AI is going to solve all of our problems, because I've been led to believe that it will. That said, I mean, we know that AI is consuming enormous resources. So I was just wondering your thoughts on, is AI going to be a positive thing for solving these problems, or is it going to be part of the problem?
That is such a deep question that actually Tesla mentioned, I'm a founding member of a faculty activist group on climate. And one of the topics that we're talking about is a future discussion on campus about, is AI worth it given the energy use? I'm extremely concerned about this. When you look at the energy use of AI, it's creating a lot of extra carbon emissions. It's putting huge stresses on our energy grid, on water resources. Is it worth it? Personally, I will go on the record, I don't think so. It's leading to loss of jobs. It's leading to all my students cheating on exams. It's summarizing my emails in ways that doesn't really work. I don't need the summaries of those emails. I have a brain. I can summarize it myself. I personally don't think it's worth the energy use. And so this is where, as a planetary species, we need to come together and actually talk about resources and our use of resources. Is AI worth the energy resource that it is? And we need to have a say, not just the big companies dictating that this is where we need to go.
So now questions online.
Yeah, we have a couple of questions regarding dark matter. I think mainly, how can we detect it if we don't know what it is? And why do small galaxies have so much of it?
Oh, right. Okay. So how can we detect it if we don't know what it is one of what I did in my PhD. So this is the thing that I know a lot about. This is what I work on, and Sven actually also works on. It's called gravitational lensing. And we have Earth here. Let's see if I can get my pointer back again. Earth here, and then a distant galaxy. A large amount of dark matter. Dark matter is a mass. We looked at the equations of general relativity. We said a mass curves space-time. So a large amount of dark matter curves underlying space-time, and light will follow that curved path. The light now travels in a curved line from this galaxy to Earth. This leads to an effect that is visible in galaxies. So this stretching of light here is gravitational lensing. And by measuring this stretching, we can infer how much dark matter there is in the middle. So this is one of the ways in which we actually go out and study and measure the amount of dark matter with observations. Now, the second question was, why is there so much dark matter in little galaxies? I would actually turn that around and say, why are there so few stars in little galaxies? And that's because galaxies are made up of stars and hydrogen gas and dark matter, but little tiny galaxies, for reasons that are still being debated, didn't form a lot of stars. So they still have lots of dark matter in relation to their stars, whereas more massive galaxies formed a lot more stars. They were more efficient at forming stars. Thank you, Zoom.
There was another question.
On Zoom or in person?
You had said there was another question on.
Well, I have a bunch, but yeah, we can maybe also say, is there a dark equivalent of E equals mc squared?
That's a question for Tesla.
Well, I mean, it's anything with mass. I mean, mass is equivalent. Basically, that statement is saying mass is a form of energy. So anything with mass, including dark matter, would
Right.
follow the same equation.
Right? That's right.
I just wanted to go back to your the issue of pedagogy and
Yes.
sustainability.
Yes.
My wife, a banana slug, teaches down at USC. They've been much more sensitive to the pressures of the Trump administration. And so and she's in the policy school, and they've had discussions, and people in the administration are coming into their faculty meetings and saying, we need to be more open and sensitive to the views of conservative students. And so people were kind of throwing out, well, what do we have to entertain? What would you respond to them when someone says climate change is a hoax? This is the evidence isn't there. I don't believe it. So why are you telling us that I have to use 5 times less resources in the future of my life?
Yeah, I would tell them that there's no debate on the science of climate change. And I would show them some of the graphs. And I would step through those curves of varying CO2 levels and how they're so high and talk about the physics of it. And then I think we can reframe it as, scientists know that this is true, this is a genuine thing. The real debate is about resource uses. It's about whether we want to use those resources now at the detriment of the next generation, or we want to distribute those resources in a way that future generations will use them. It's also a question about resource use in terms of wealthy countries versus less wealthy countries, and wealthy people versus less wealthy people. Because many of the people making these decisions are incredibly wealthy and will not be as affected by these effects. But let me be very clear. Everyone will be affected. But clearly, wealthy people will be affected less than others. So we need to reframe it as a planetary level discussion on resource uses. And the people who want to debate the science or who want to debate, it really boils down to lifestyle change. People don't want to give up their yachts. People don't want to stop going on holidays. People want to continue our current lifestyles. And that's the debate we should be having is that how we want to spend our resources?
Kind of a related question, and I'm not trying to argue with you because I agree with everything you say, so it's maybe how would you argue with other people.
Yeah.
But some of us who are really old remember reading a book in our teens called Limits to Growth, where they did some linear models, and people who read it says, wow, it's really bad, civilization's going to collapse. And it didn't happen. Okay, so apparently they did have plans Bs, and I think it really was because, the world is not linear, right? How do you tell somebody who says, this has never happened before, based on all these scenarios, what do you say and why is this different? Why is it different this time?
Right. So the thing that they failed to take into account for limits to growth was the improvements in agriculture. So we have gone through a green revolution with many improvements in agriculture, creating artificial fertilizers. And so that has been able to feed our growing population. I think it's estimated that the process that takes nitrogen out of the air and creates fertilizers has led to at least the ability of half of you being here today. But if you go out and look today at our ability to grow food over, if you fly from here to the other side of the US, it's fields everywhere. So we are running out of space. We also will eventually run out of phosphorus and other resources. And in addition to that, we'll be facing climate extremes across the equator. So we're going to run out of food-growing regions across the equator. Even further north or further south, where we are able to grow food, we're going to be subject to a lot of climate variations. There's nothing a farmer likes less than conditions that they can't predict. Stormy one day, drought the other day. So those realities are going to come out and hit us. And I think the limits to growth idea was fundamentally correct, except it did fail to take into account this green revolution. there's not a whole lot more we can squeeze out of agricultural technology for growing food in the industrial model.
So I believe there's a question over here.
Hi. I have two questions, if
Yes.
that is possible. One is dark matter, dark energy related. In the beginning of your talk, you mentioned that dark energy and dark matter are quite different and that maybe it was a nomenclature mistake to name them. Is there a similar relationship between the two as there is with energy and matter in our sort of the universe that we interact with on a day-to-day basis? Energy, the E equals MC squared kind of thing. Are those connected in a similar but different way for the dark energy? Or should I not be thinking about them that way?
It depends on the physical models for dark energy. In the most simple form that we talked about, dark energy might be associated with an energy of the vacuum, energy of empty space, so which is actually a very interesting question. What is the energy of empty space? In which case, there would be a correspondence. There are particles jumping in and out of existence in empty space. There's a correspondence between mass and energy of empty space. But there may be other models of dark energy that have fundamentally different behavior, in which case it would be different. Do you want to add anything?
Well, I would just say, I mean, there are different types of forces. Like there's gravitational force, there's electromagnetic, and some particles feel both. Like, you know, electrons feel electromagnetic forces. They also have mass. They feel gravity. And so in the same way, like dark, you know, these could be like fundamentally new particles, new forces, and they may or may not then connect.
And some models have dark energy interacting with matter and some don't.
Okay.
So, yeah, it comes back down to our current ignorance.
So we just don't know enough. Okay.
Yeah.
The second question, real fast, was a follow-up on how we decide as a species to utilize resources.
Yes.
There's some studies that have shown recently that the human mind regards our future selves as a different entity. Like what parts of your brain light up when you're thinking about yourself now versus yourself in the future, even though it's still, oh, you know, what am I going to be doing next month, or how am I going to pay my rent, or whatever. Future self is different. So if I'm trying to convince a population that we need to possibly utilize our resources differently and do less now, it's sort of, even though I know I might have a hangover tomorrow, right now I'm hanging out with my friends and I want to have another glass of wine or stay a little bit longer. Future self's going to deal with that, not me.
Yes.
How do you address that part of the issue of getting the human mind to be better at connecting the two?
Yes, absolutely. I'm not a psychologist, so I don't know, but that's a huge part of the problem. And in fact, in some of the projections from, for example, the IPCC, the Interpanel Government on Climate Change, some of those predictions assume magic wands that in the future, a young gentleman down here is going to fix stuff for us. So it's not only just us in the future, it's also our children. You know, we think differently about our children in the future and the next generation. How do we overcome that? I think one is through education, one is through talking about it, events such as this. But in addition, I also think that one of the greatest challenges we face is we are stuck in this current economic system. And it's the economic system that's driving growth and driving increased CO2 emissions, AI being a fantastic example. Companies are pursuing AI because they see profit and they need to grow. So that's a model of our economic system. It doesn't have to be that way. We could have other economic systems. There are societies on Earth that have lived for thousands of years sustainably. A big challenge is that we're stuck in this system and we don't see a way out of our economic system. And that's where we need to have an interdisciplinary, high-level process, talking with our economic colleagues, with our political colleagues across the board, our psychologists.
Let's go back to online.
Maybe I can ask one hopefully quick question, which is home composting does not create methane like in landfills. Could you maybe elaborate on that?
It depends on how you do it. So ideally, the methane is generated when you have an anaerobic process. So if you have a giant compost pile and you're not keeping it oxygenated, you would create methane. So ideally, in your composting process, you turn it or you mix it or you have a small pile and you keep it aerobic, in which case it doesn't generate methane. And if you do it at home, you have the added benefit. You don't have to buy compost from the store, and it works really well, and you can grow strawberries and salads and delicious things.
If I can joke for a second,
Yes.
when I was a kid, we had a compost pile, and we accidentally grew pumpkins from
Yes.
our pumpkins from Halloween.
Yes. Free pumpkins.
Yeah, free pumpkins, exactly. Oh, yes, please.
Yes, I had just a technical question from the sensors and measurement perspective. This is a dark matter. Dark energy is something that isn't easily measured, but there was a slide that had, I don't know, it's a $100,000 filter or something. Can you describe how sensing works, what that thing does? And
Yes.
whether it's a proxy, convert something you can't measure into something you can, or kind of
Yes.
how that works.
Those filters are actually not designed to find the dark matter. They're designed to find the little tiny galaxies. So the first step in this process in that project is to find these little tiny galaxies. And they are hard to find, and even harder, they're harder to find out the distance, how far away they are. If something is really far away, and very bright, you could confuse it with something that is closer and not so bright. And we really wanted to distinguish those two. So we need to know the distance to that little tiny galaxy. Yes, so the filters are designed to detect the redshift of the galaxy. Once we have the little galaxies, then we use this gravitational lensing technique around the little tiny dwarf galaxies to find their dark matter. So yeah, does that answer the question? Yeah.
I think. Oh, no. Oh, over here. Yes, of course. Thanks.
Thank you for interesting presentation, and my mind has so many questions, but I'm trying to, interest of time, will ask you. So as a human, we are different people, and most of our growth has come from us being creative, greedy, lazy, and all the other properties that we have as humans. When you say there is a limit on growth, how do you convey that there is a limit on growth on a mind which wants to grow, which is creative, which wants to find more solution, which wants to do something more different? And the second part of my question is you are talking about solutions at a species scale. But we are, by general definition, we are very local. We live in small ecosystems, etc. So a solution that is at a species scale may not scale. How do we solve for that?
Okay, those are two very profound questions. Thank you. On the first question of creativity, I think we have a lot to learn from indigenous peoples. And again, in the same way that we're stuck in our little tiny moment in cosmic time and we can't see beyond our boundaries unless we learn and educate ourselves, we are also stuck in an economic system and a societal system that doesn't have to be the way it is. I remember a quote from, I forget which indigenous group, but someone asked them, I think these were people living in the Amazon, like, why don't you grow fields? And the answer was, well, I have enough monkey nuts, so why would I grow fields? I don't need that. And so there are solutions to this that humans have used in the past and still currently use in many societies, but we all here in this room are stuck within a mindset and an economy that's hard for us to change, but we can change it. We can work with our children, we can work with ourselves. And then your second question was about local versus global. Well, I really like this book. So this is about local solutions to suburbia. And I find it very practical. I don't agree with everything written in this book. I can tell you some things I don't agree with it. But there are a lot of local solutions: composting, rainwater harvesting, using less, growing your own food, a lot of things that would help change our mindsets. But I very much agree. I think we need to prioritize local economies. At the same time, we need a global vision and global cooperation. And I think our biggest barrier to that is wealth. Our biggest barrier is we have a pursuit of wealth individually and as countries. And unless we give that up, we're not going to get out of this. Yeah.
Okay, so I'm told we have time for one more question. We've taken fewer online, so I'm going to go to Sven for online questions, and then maybe Alexie will stick around for a little bit afterwards.
Maybe the last question is, do you feel hope for our species and our capacity to transform into a planetary species, and how does your work connect to that?
If I didn't feel hope, I wouldn't be doing what I do. And I also have children, so we also, I do my work for them as well. I do think we're extremely creative, as you mentioned. I think there are many solutions. The biggest barriers that we face, I believe, are our economic system and our current lifestyles and our polarized politics. So unless we can tackle those, then I'm not very optimistic. But if we can tackle those, and that I think requires a huge amount of citizen engagement. I think we need large levels of citizen engagement. That means all of you voting, demonstrating, acting, joining groups. The huge challenge, the greatest challenge that we face is a problem of time scale. I actually didn't mention this, but the reason I talked about cosmic time is because you saw that huge spike of CO2. The issue there is that that spike is so unusual and so fast that we now have very little time to act. So we have decades to turn this around, which is incredibly short, which is why I've transitioned a large fraction of my research now to sustainability, because I don't see a future on our current trajectory where we're continuing to do astrophysics and where my children will be able to do astrophysics. We won't have that luxury. So we need to change. And if I can turn my profession around, you all can go and do something too, change something. Sign up for an organization, look at solutions, but it is incredibly urgent. Yeah.
Well, thank you both for a fascinating
Thank you.
And thank you all for coming tonight. Please join us on December 3rd when Professor Javier Gonzalez Rocha will be speaking on Raising the Unseen, how drones and good sensors reveal the hidden air quality impact of climate change. Good night, everyone.